So if you remember from chapter 3, we were discussing polarities of bonds. And in particular, we were looking at polar covalent bonds in which there is an uneven sharing of molecules between mostly elements of different, starkly different electronegativities. Now, the electronegativity values that we tried to um, that we were looking at before were something around the range of 0.5 to 1.7 difference in electronegativity. If it's too much, then we have an ionic compound. If it's too little, less than 0.5, then we have a nonpolar covalent bond. But otherwise, in between, we have polar covalent bonds where there is just an even sharing of electrons. Now, that is just talking at a local scale, meaning just individual bonds. Now, if you have, on the other hand, if you're discussing or if you want to talk about the polarity, the overall polarity of the molecule, then that will just be the sum of all of those bond dipoles. Okay, dipoles is basically what arises from an even sharing of electrons due to differences in electronegativity of atoms bonded to each other. And the sum of those bond dipoles in a compound, in a covalent compound, will result again in the permanent dipole, which can be measured by a dipole moment. We're not going to go into the nature of this experiment, but basically it involves some magnet and it involves basically an electric field as well, an application of the electric field, that is. But one thing that you should remember from chapter 3, this sign delta positive just means you have an electron poor region, or the electron density is low around hydrogen. Okay, so remember there's two electrons being shared between hydrogen and fluorine, but since fluorine is the most electronegative element, this part is actually electron rich. Okay, so again, these partial charges are not really equal to an actual charge like ions, but it's just as a result of an even sharing of electrons. Now, let's consider, for example, two bonds. Okay, so if you have, for example, a carbon-oxygen bond, then you would expect carbon to actually be less electronegative than oxygen based on Trenson periodic tables. Okay, carbon here should have, therefore, a partial positive sign and oxygen a partial negative sign. But if, for example, you have two carbon-oxygen bonds, such as in a carbon dioxide, a linear molecule, remember that the structure for, or the, rather the structure, but the number of electron domains in carbon dioxide is 2, so you have two double bonds, and therefore it should have a linear electron pair and molecular geometry. So if this is one carbon-oxygen bond or one carbon-oxygen double bond, so still this part of this carbon atom will still be electron poor, and this oxygen will actually still be electron rich. Now if again we have another oxygen molecule here, and you actually have another double bond with carbon, then this oxygen is also electronegative. Okay, more electronegative than carbon, that is. And you have here an electron-rich region as well. Now these dipoles, I mean, since this carbon-oxygen double bond and since this carbon-oxygen double bond are identical, they actually are equal in magnitude. But notice that because of the linear structure, these dipoles are actually pointing at opposite directions. And when I say pointing in opposite directions, basically the negative end of the dipole. As a result, when you actually get the mathematical sum of these dipoles, they actually cancel each other. And even though carbon dioxide has polar bonds, it is considered a nonpolar molecule. Okay, nonpolar molecule. Okay, on the other hand, if you have structures like water, okay, so water has a bent structure. Remember that water has two lone pairs here, which actually contribute to its electron pair geometry being tetrahedral. Okay, so for water, there's actually two OH bonds, and both of them are actually pointing at this direction. Okay, so hydrogen, and this is oxygen, and this is another hydrogen. Okay, and as this cartoon illustrates, there's, unlike carbon dioxide, there's no bond coming from this direction to cancel out this bond, and there's no bond as well coming from this direction, or no OH bond coming from that direction to cancel out this bond. So if you add these two dipole moments mathematically, we'll actually end up with the net dipole of water pointing upwards. And as a result, water is actually a polar molecule. It's a polar molecule with polar covalent bonds. So, as you can see here, a molecule can actually have polar bonds but still be nonpolar. Basically, if those dipoles are pointing in the opposite direction but are equal in magnitude, and that's usually achieved if you have two similar bonds pointing in opposite directions and they cancel each other out, basically, if you mathematically add them together. And then if nothing cancels out, then you have a polar molecule. Okay, so for example, HF, that doesn't actually have anything to cancel that dipole moment in the other direction. Okay, so this is polar. Okay, you have water. We've just discussed this before. Okay, we have ammonia. So all of these are actually also pointing upwards. So this one has an overall net polarity pointing upwards. Before we go to trichloromethane, so let's consider first, for example, methane. Okay, so methane, as we know, has this Lewis structure. Okay, it has a tetrahedral structure. Now, methane should have no polarity. So methane is actually a nonpolar molecule because it's just comprised of CH bonds. But what if, for example, we have carbon tetrafluoride? So for example, this, okay, carbon tetrafluoride. And again, I'm not going to write the Lewis structures, or sorry, the electron pairs around fluorine anymore. Okay, if we have carbon tetrafluoride, okay, so these two will actually cancel each other out. So we have the net dipole pointing towards this direction first, not net dipole, but dipole moment of that bond, and then another bond dipole pointing that way because fluorine is more electronegative than carbon, and then another bond here, and then another dipole pointing towards this direction. It's hard to see here, but this dipole actually is equal in magnitude but opposite in direction with this dipole, and therefore they will cancel each other out. Okay, and this dipole, okay, will cancel out this dipole. Okay, so carbon tetrafluoride, or meth, is actually nonpolar. And again, we established earlier that methane is also nonpolar. Okay, now if, as you can see, all of the four bonds there around carbon are actually the same identical atoms. So if, for example, we have trichloromethane, okay, so it's basically like methane, but instead of 4 hydrogens, you have 3 chlorine atoms instead. So notice that trichloromethane only has 3 bonds which are similar and still has this hydrogen-carbon bond. Okay, so for this one, these 2 bonds equal in dipole, but equal in magnitude rather, but opposite in direction, will cancel each other out. Okay, but for carbon, this carbon-chlorine bond, this one actually does not really get canceled out. That's why the overall direction of the polarity for this molecule is towards that direction, okay? And therefore, trichloromethane is actually a polar molecule, okay? The same thing can be said, for example, for this molecule. If instead of having 4 chlorines, you have a fluorine, then these bonds, remember, will cancel each other out. They're pointing at opposite directions. Now, you have this time a carbon-fluorine bond and a carbon-chlorine bond pointing at opposite directions. Okay, now you have to think here which between fluorine and chlorine has a higher electronegativity. So between carbon and fluorine, okay, fluorine actually has a higher electronegativity. So to some extent, this carbon-chlorine bond will actually cancel out some of the electron pull from this carbon-fluorine bond, but not that great because fluorine still has a higher electronegativity. Basically, this bond again has a higher change in electronegativity value than this bond. So therefore here, this molecule will be slightly polar, but nonetheless, if you're asked in the test, is this a polar molecule? Then yes, it's still a polar molecule. Okay, so when determining overall bond polarity, it's actually important for you to know first what the Lewis structure of the compound is, so that you can determine what the molecular formula is. And then from the molecular formula, again, the molecular formula, not the electron pair formula, or electron pair geometry rather, molecular geometry and electron pair geometry. You can determine from the molecular pair geometry whether those bonds cancel each other out. If you have bonds which are similar to each other, let's say, for example, carbon dioxide is something that we have discussed earlier. If you have sulfur trioxide, okay, again, these are bonds which are actually polar too, but all these 3 cancel each other out. Just because this one and this one will add up to a net dipole pointing downwards, and then this dipole will actually be equal in magnitude to that average. Okay, so those dipoles actually cancel each other out. Okay, and you also have, we have discussed this before, carbon tetrachloride. We have discussed carbon tetrafluoride and methane. But this one, again, similar to methane, or sorry, not similar to methane, but similar to carbon tetrafluoride, will have 4 polar bonds, but overall it's not a it's a nonpolar molecule because those bonds, dipoles, will cancel each other out.